Okay, so this one is on the chapter, the second last chapter, magnetism and electromagnetism. Now, first of all, we need to understand a little bit about magnets and magnetic materials that are attracted by magnet. And later on, we talk about electromagnets, all right, current producing magnetism. So what's a magnet actually? Magnet is a very special object. It has this magnetic force. So a magnet is a special object that can attract or repel other magnets. And it can always attract magnetic materials. Magnetic material has no pole. So regardless of which pole is my magnet, I still can attract the magnetic material. All right. So magnets are used very widely. For example, in refrigerator. Okay, magnets is used in motors and so on. Motor is like, for example, little motor, we apply electricity to it, then the thing will move. Propeller motor or rotating motor and so on. Okay, what's magnet? Magnet has two poles. There's a south pole and a north pole. And like poles repel, unlike poles attract. That is about magnets. And both poles attract magnetic material. So magnetic material, regardless, it has no pole actually, until you become magnetic. So in other words, if I put like this, if I put a magnet north, south, if I put a magnetic material here, this will turn to north and south. Even when I flip it, it'll still be north and south, north nearer to south. Is it okay? It's called induced magnetism. So you must understand that magnetic materials are attracted to magnets, but non-magnetic materials are not attracted to magnets. So very interestingly, this one, aluminium, copper, they are not magnetic. They cannot be attracted by magnet. And of course, other non-metals are non-magnetic. The magnetic will be things like iron, steel, nickel, cobalt, and so on. These are all magnetic material. They all can be turned into magnet. If you put a magnet on it, they become magnet themselves. Okay, so magnets used, like for example, in the fridge. Okay, magnets used in motors and so on. Yeah. So you need to understand a little bit about magnetic domain theory. What's magnetic domain theory? So basically, you need to understand here is that the domains are like those tiny magnets. Okay, wait. First of all, I think I better explain this. I use a yellow color because it's not very important, but need to know. Each atom behave like a miniature magnet. Okay, and they can spin. So the atoms can align themselves into groups called the magnetic domains. So when the domains are all aligned, they become magnetic. All right, so this magnetic, this is also magnetic. This is a very strong magnet. This is a medium strength, and this is not a magnet. Why? Because generally the alignments are quite aligned in same direction. So you realize I got a north here, I got a south here. Okay, this one is in a mess. There's no north and south, so it's not a magnet. Is okay? So you just imagine in a piece of magnet, there are millions and millions of these. If they're all aligned up, means it's a magnet. If it's not aligned up, it can still be a magnetic material. If you put a magnet near to it, they will align up by itself. So if you have this material, you put a magnet north and south, or put a magnet near to it, all this orientation will start to point towards the magnet itself. Is okay? So magnetization is the process of making object become magnet, and it's actually aligning the magnetic domain. The purpose is align all the domain as much as possible, so become a stronger magnet. If it's totally aligned, means a very strong magnet. So a very strong piece of magnet has most of the domains aligned in one direction already. Okay. So okay, that's not okay. Like this, you put a bar magnet. This end nearer will induce. Induce means that you produce a south pole without touching. You induce to be a opposite pole. Okay. So what happens is the strong magnet will force some of the domains to align, and therefore magnetizing the iron bar. So the iron bars near the magnet's north pole become south pole because of the alignment. Okay, you align in one direction. So it becomes north, south, and so on in one direction. And we also can induce magnetism by putting it in the current carrying solenoid. So what is this solenoid? Look carefully, the current flow to the back, to the front, back to the front, back to the front, back to the front, and so on. So all these are current flow in one direction, it produces magnetic effect. So a solenoid is just a coil formed by many turns of the insulated wire. So these are the different turn, and then you switch it on, you produce magnetism. One side north, one side south. Any question?
No.
Okay, are you getting lost?
No.
Okay, so how do you induce a magnet? Of course, in this case, how to create induced magnet? Of course, you can just take a piece of iron, you coil the what do you call that? You coil the wire around it. All right. So when current flow in the wire, it becomes a magnet. So how to create induced magnet? So you can wrap some insulated wire around an iron bar to form solenoid, and then connect to a DC. It must be a DC. Okay, around the iron bar, and the current carrying solenoid will behave like a magnet. Okay. So down here it says that switch off this iron bar by right should lose magnetism. I try not to use iron, soft iron. Soft iron will lose magnetism. In your syllabus, you must know that. So I try to change it to the steel. Say steel. The magnetism. Be careful of what you write. In simple, in the syllabus, if you say iron gains magnetism very fast, lose magnetism very fast. You switch it off, you lose its magnetism. But a steel bar, steel is made for iron, but it's not pure iron. It maintains its magnetism. Is okay? Now, how to find direction? I use a right hand grip rule. All right, I can use a right hand grip rule. Right hand grip rule. So what does it mean? When my finger is the current flow, my thumb points the north, up from the north. Can you align with me? Can you put a hand up and then you try to imagine the current flow from the back to the front? You see that? Go to the back, come to the front. Go to the back, come to the front. Like that. Forward. So the north is on this side. North is here. Because the current flow from the back to the front, you see this? Imagine you have a pencil, a pen, you wrap from the back to the front, the current flow from the back to the front. Finger is current, and the north pole is the thumb. Okay? So in right hand grip rule, I will say fingers are current flow. And the thumb is north pole of the magnet. So it's right grip rule. Okay? That's all. Is it okay? Yeah. Okay, so or you can look at the pole from this side. You look from this side, it looks like a north. Based on the coiling, if it come to the front means coil anti-clockwise. Look from this side, it's coil clockwise. Anti-clockwise flow is north pole. You look at this side, if it's clockwise flow, it's called south pole. If it's clockwise flow. Okay. From the back to the front, is it? If you look at hand like that, isn't it clockwise? South pole. Is it okay? All right, so that's it for this one. Now, you must understand temporary and permanent magnet. So temporary magnet, we take it as soft magnetic material, temporary magnet. Iron temporary magnet gains and lose magnetism easily. You switch on, there's magnetism. You switch off, they lose magnetism. But for steel, okay, it retains magnetism for a long period of time. Is it okay? So if you magnetize a piece of steel, the steel will become your magnet. It won't disappear, it stay there. Okay. So temporary magnets are used to pick up to create switch the magnetic effect on and off. I guess this one. This is junkyard, the scrapyard. They use magnets to attract the magnetic material like iron and steel. Things like aluminum cans and so on, they will never be stick to it because aluminum is non-magnetic. And permanent magnet is used in places like fridge door, Okay, or electric motor, you have the electric motor I highlight for you. Electric motor, you use permanent magnet, or magnetic door catch or freezer or refrigerator. All these are permanent magnet. Okay. All right. So we will go to here. Look at this. This is the bar horseshoe magnet. Now you must understand horseshoe magnets are there. One side north, one side south.
Wait, how does the scrapyard magnet work?
The square magnet actually is a coil like that. This iron with a lot of the coil is on iron, so that when you switch on the current, it become magnetic. So
But you
become
can't see the
magnetic.
coil.
Huh?
But you can't see like the coil.
Yeah, I cannot see it's inside lah. Yeah. You know what I mean? Okay, it could be like that. I don't know. It could be like that. Could be a big disc kind of thing, you know. When the wire goes in this way, look at it. My wire goes this way, it goes around that. You know what I mean? And then go out this way. So center is actually the chain that pulls it DB up. Okay, or the side I don't know. But as long as you got current flowing through, this whole thing become magnetized. And then you attract other magnetic material. Okay? Yeah. All right. Here. I'm explaining this one. Okay, why can the nears which are in contact with the magnet attract other nears? Look at this. When this iron is near to it, it will form a south pole and a north pole. Induce opposite pole and then it attract. Here induce opposite pole, a north pole and a south pole, and then it attract. Am I right? Look at the second piece of wire here. Isn't it a south pole here? I use another color. A south pole here and a north pole here. Am I right? And here could be a south pole here and north pole here. Yeah, that's how they attract each other. Okay. So down here is south. I will say that then it could be a north pole here and a south pole here. See the point? And then this side is a north pole here and south pole here. Okay, wait, let me think. Yeah, correct. North attract to south. Yeah, correct. North attract to south is correct. Yeah, so that's how it looks like. So why can the nears in contact with the magnet attract other nears? Why my first near here attract other nears? Because they have become what? All of them become what? Induced magnets. They are becoming magnet, having magnetic property already, and therefore can attract other nears on their own. Okay? I repeat, they become induced magnets. They become magnet already, and they can attract other magnetic material. And state whether after the magnet remove, some of the nears still attract to other nears. Whether the nears are made of hard or soft magnetic material, hard means hard to lose. Answer is hard. Because hard magnetic material means imply difficult to lose magnetism. Difficult to lose magnetism. Any question on this?
No.
So when you talk about hard magnetic material, you think of steel. You think of permanent magnet. Soft magnetic material, you think of iron. Easy to magnetize, easy to demagnetize. Okay? All right. Okay, let's try this question. Try this question.
I don't get it.
You don't get it? Okay. X and Y are exerting attractive force, magnetic force on each other. Which one is not possible? Can a magnetized magnetic material attract another magnetized magnetic material?
No.
Of course can. Magnetized magnetic material is magnet what? Magnet attract magnet is correct or nothing wrong what? How about this one? Magnet attract unmagnetized magnetic material, can also, right?
Yeah.
Unmagnetized attract magnetic,
Yeah.
can, right? Can a magnet
Oh
attract
no,
a
D.
non-magnetic? Answer is D, yeah? Because this can never be induced magnetism. Okay. All right, let's move on here. Okay, magnetic field of bar magnets. So memorize the definition. Put a star there and memorize it. A magnetic field is a region in which a magnet or magnetic material experiences a magnetic force. Region, a magnetic material or magnet experiences a magnetic force. Any question on that?
No.
So you put a magnet within a magnetic field, you'll be attracted or repelled. It must have a magnetic force. So if you pour iron powdings on a piece of paper below, put a magnet, right? You realize actually it formed this kind of pattern to show you where are the field lines, magnetic field lines. All right. Okay. The iron powding experience magnetic force exerted by the bar magnet, and then they all align to show the direction of the magnetic field. Okay, or you can use a compass to determine direction of magnetic field. Put a compass plotting. You realize that I put a compass here. I put this position and mark out the first dot. Then align the tail to this one and mark out second dot. The needle was like that. Needle is like that. Needle is like that. You see the point? I'm using the needle as I move around it to show me the direction of the magnetic field lines. Any question?
No.
No? All right. So this is just an explanation how I do it. Now remember the magnetic field pattern. Magnetic field pattern. Okay. So the lines here is closer. You see the lines here are closer. Lines here are closer. And as you move away from the poles, the lines are further apart, means weaker. Here's closer means stronger. The few lines closer means they're stronger. And it's actually in a symmetrical shape. Magnetic field line, magnetic field line, magnetic field line, magnetic field line. Okay?
Mm.
Do you know how to draw this?
Mm.
You must know how to draw this, huh? Okay, I show you very simple. First, I draw a magnet. North-south. I know north must be out, south must be in, like that. That's all. You know what I mean? And then I do this. I do this very white one. Oh, this is wrong one, sorry. Not nice. I do this white curve out. Okay. Yeah, go out. And I can this thing, right? You see the point? Oh, sorry, I cannot touch. Remember the line cannot touch, right? Now touch being gone already, yeah? Like that. Make sure the line don't touch. Okay, I can expand a bit out like that. Okay, look at this. I'm gonna have few lines from here, go to here. See the point?
Mm-hmm.
My drawing is not good, definitely not good. Yeah. So it's like that. Okay. So the magnetic field come out from the north, enter from the south. And these are the magnetic field of the bar magnet. Okay, how you do it? How to find this thing? In fact, you put a piece of paper over this, you pour iron powder inside. On the surface, it become like that. You can see the magnetic field lines. Okay.
Mm.
All right. So, field pattern between two bar magnets. North point to south. Remember, this one, don't forget. North point to south. This is the key thing. And then the rest just draw like that. Okay, it curves like that in. Okay. And if both are north, then there's a neutral point where the lines cannot cross. And north try to go to south, the north try to go to north, this also try to go north, you push against each other, become like that, the few lines. You need to practice a bit of drawing few lines. Make sure that the lines do not interact, do not cut. Okay, so I write a note for you. Magnetic few lines. Okay, where are you?
Yeah.
Do not cut. one another. Okay, so remember that magnetic field lines do not cut one another, or else the drawing will be wrong already. Is it okay? Right. So the exact middle here is called neutral point. Neutral point where there's no magnetism there. Okay? Right. Oh, are you okay?
Yeah.
Right. The needle of compass always point towards the north pole of the magnet, or south pole of the magnet. Of course, point to south pole. Because the needle compass is always north. I repeat, compass needle, their needle. And therefore it points not to the north, but point to the south. Here, point to the south. You okay? Yeah. Right. All right, here you need to understand this thing. Let's look at two phrases. Magnetic south pole. You see that? This side is a magnetic south pole at the bottom. Repeat, south pole on top, north pole below. So we say that in North America, but actually it's the south pole. I repeat, north is here. We can't say that, oh, this geographical north, on top geographical north, China is north of Singapore, am I right? But below actually is the south magnet. Okay, so our Earth, on Earth, our magnetic needle is a north tip, north pointing to the south of the magnet, Earth magnet. Okay. Any question?
No.
Okay, so if it is a north pole here because it is attracted to Earth magnetic south, below is a magnetic south, okay, which is geographical north. And why some species of migrating birds uses how do some uses a magnetic field? Because the bird migrate, they don't look at the sun, okay, but they look at they feel the magnetic field lines. So they can fly very far, use the Earth magnetic field line to indicate they find the correct direction. Very interestingly, their brain has this magnetic thing can detect the north field lines. So they follow and fly up. And then the winter they fly down. And so on. Is it okay? Right. Okay, let's try this question. Okay, what do you think is the answer for this? The field line became from the pole X to the pole Y. It means like that.
B.
Right?
B.
Can't hear you. D or B?
B.
Boy?
Mm-hmm.
You see, I draw for you already. X to Y, isn't it north to south? Okay, that's good. All right. A little bit more, I'm going to end with this part. Wow, okay, I think we can't finish the whole thing, but I'll teach you how to read the thing first. Just now we talked about current and this magnetic field, direction north, right? The thumb is north. When the finger is the current direction flow, round and round, this is the north. On the other hand, if the current flow is thumb, then the finger is a magnetic field, the circular magnetic field. Okay? So this against the right-hand grid rule. So when fingers are current direction, okay, the thumb is north pole. So this is the first case. Now, when one finger only, okay, when the thumb is current direction, Then the finger is magnetic field. Okay, do you realize it's the opposite? Okay, if this is the current, then this is the thumb is the magnetic field, the north. But when the thumb is a current, then the earth is a magnetic field. Go round and round. So there's something called the circular magnetic field. Okay, what like that? Okay, like that. Okay. There's a circular magnetic field. Is okay? When current flows up, there's a circular magnetic field. So I put down here for you. Current flow like that. Flow like that. Then circular magnetic field around the current. Any question?
No.
No, huh? All right. Okay, let's look at this thing. If I'm using, if I have a stronger current, then the magnetic field will be more. Okay, so when you use a magnetic or current, the magnetic field becomes stronger, more rings. When you reverse the direction of the current, the magnetic field reverse direction as well. So imagine the current points down, your thumb points down, the magnetic field goes clockwise. Are you with me?
Mm-hmm.
You have to focus. I think you're a bit confused. Are you confused?
Okay lah.
Okay, please pay attention to this. So remember what I say? Thumb is a current, finger is a magnetic field. Okay, that's what happened here. And increasing current means stronger magnetic field. Change the current direction means change the magnetic field direction also. Okay? So this is the rule. Current is the thumb, earth, the finger is magnetic field. So if you look carefully, this one means dot means the current coming out or magnetic field coming out from the paper. Okay? They note this direction is out of the paper towards you. Like that. Looking at it, point to you. If it's a cross, it's going in to the paper. Direction is into this page. So dot is out, cross is in. I repeat, dot is in, out, dot cross is in. All right. So this is a current flow. Can you look carefully? Can you tell me the current flow out or in? This case, out or in? First one, here. Out or in?
Out.
Out, right? Yes, dot is out. So imagine current flow to your face. So isn't it your finger, the circuit anti-clockwise? You see that? Can you use your right hand to show me how it looks? The current coming out through your thumb, the finger is a circular anti-clockwise. Can you put a hand on the screen like that? Right hand grip rule. Thumb is current.
How? I don't know.
Take a thumb, point your thumb at your face, point at your face. Point means out. The current coming out through the thumb to you. So my finger, is it clockwise or anti-clockwise now?
Anti.
Anti. Look at this here, this anti.
Yeah.
So when the thumb shows the current coming out, the magnetic field is anti-clockwise. How about the second one here? The current is going in. I need to put a finger pointing into the paper. So my finger will be going around the clockwise direction. Yes, correct. That's what they mean. Okay? Can Okay, good. A little more. So the thumb in the right hand grip rule points in direction of convection current. Yes, current flowing out. So this is thumb, not the electron flow, because electron flow is opposite of convection current. I repeat, electron flow and convection current opposite. Electron flows in opposite of convection current. It's okay? Yeah, that's it. Can I? Okay, next one. Imagine this is the coil or wire. All right, one side out, one side in. Out means you put your thumb, point out. Is it correct to say this is anti-clockwise? If it's out. Okay, use a right hand grip rule. Right hand, point out the thumb. It's
Yeah.
anti-clockwise.
Yeah.
This side is going in. You see the in? This side is in. One side is out, one side is in. So this side in, this side out. Am I right?
Mm-hmm.
In, you point your thumb in. Do you see that it's clockwise? Your thumb, your fingers. Can you try?
Right.
Your thumb point into the paper.
Like that.
Yeah. So does it look like it's clockwise rotation of your magnetic field?
Yeah.
Yeah. So it's all. So that's what it means. One side in, one side out. You produce a magnetic field that looks like this. Okay. Very interesting magnetic field, right? Okay. Next one. A solenoid like that, a coil. The current flows. Now the current flows in a circular ring. You see current going in here, go to the back, right? You see the wire? The current flow like that. Follow me. Current flows here, flow to the back. You see that?
Mm-hmm.
Go to the back. So can you put a finger? Finger is current flow now. And the thumb is a north. Yes, it's correct. It's a north. If thumb is current flow, finger will be magnetic field line. If finger is current flow, the thumb is magnetic north. There you are. Think and then ask me you got question. Okay, I want you to use right hand. Use right hand. Can you show the like that? Current going to the back. Imagine this is a solenoid. Current go to the back like that. Isn't this the north? The north is right, the north is on the right. The left, north is on the left.
Yeah.
Right?
Mm-hmm.
The south is on the right. Yeah, so that's how you do it. Okay. All right. So how to increase the magnetic strength here? How to increase the magnetic strength? This is very strong. You see all the lines are quite closely packed, so it's quite strong. How to increase this north and south to be a stronger electromagnet? So of course, first thing, increase the current. Okay, increasing the current, increase the magnetic field, become stronger. Reverse the current, reverse the direction of magnetic field. Remember, turn it their way. Increase number of turns, become stronger also. Put a soft iron core, also become stronger. Do you realize everything is stronger except one that change direction?
Right. What do you mean?
So I want to look at this coil here, here. Current flowing from the front to the back. When you increase the current, increase the magnetic field. When you reverse the current, means current flow from the back to the front. You see that? If look at my hand, can you see? It flow north, flow to the back.
Mm-hmm.
But if you flow to the front current, then this is north. You will change direction. By having more turns here, you increase the magnetic field. By having a soft iron in the center, also increase magnetic field. So memorize, increase the current, increase number of turn, put a soft iron in the center, it all increases the magnetic field. It's okay? Okay, okay, let's move on. All right. Let me see. Okay, I tell what, this one we'll continue next lesson. I think you're very stoned already. This is application, but it's a bit more complex. I will explain this to you slowly. So we just put down here today, we end here, 20th March. Stops here. Okay, so we'll continue the next lesson. I will explain this in detail, the application. Is it okay for you? Yeah. So if you find that you cannot understand certain thing, you may want to